Hi there. In this video what we're going to do is we're going to take a look at an example, and the example is a pretty standard one in any calculus text, and what we're going to do is simply find an equation of the tangent line to this curve at this point. This point lives on this curve. You can substitute x equals 1 and see that the output is also 1. Okay, well, what is an equation of a line? Well, in Algebra 1 you probably learned a couple of different forms, and the form that I find most people are comfortable with is slope-intercept form. We have the slope and we have the y-intercept right here. But for a calculus course, especially an AP course, if you're going to be taking the AP calculus test, point slope form is probably the preferred method. They already give us a point on the line, and the only thing left to do is to find the slope of that line. So really we're halfway home with point slope form. All I need to do is substitute my point in for x1 and y1. So I get y minus 1 equals my unknown slope, that's what I'm going to find here in a minute, times x minus 1. And the idea behind this is there's some more arithmetic and algebra required to actually find the y-intercept here, and the idea on an AP test is if this works for an equation of a line, then leave it. No use to go any further than you have to and risk making a simple arithmetic or algebraic mistake. So that's why the point slope method or form is probably preferred. Okay, so how do we find the equation of a tangent line to a curve? Well, that's where our idea of a derivative comes in. And if you watch the previous two videos, you should recognize this picture. And this blue line right here represents the secant line that intersects this point and this point. Now I've gone ahead, well, let me switch these. I'm going to go ahead and I'm going to put this point, which represents x, at 1. Okay, so you can see indeed the red dot here is the ordered pair 1, 1. And you can kind of see that on the y scale, the x scale and the y scale. It's at 1, 1. Okay, this other one is h units away from x, okay, whatever h is, but we want to let h go to 0. Okay, so you can see what's happening to this distance right here. It's getting very, very small. And the closer that we let it get to 1, the closer that line becomes a tangent line. Okay, that secant line just turned into a tangent line. All right, now the slope of that line is simply going to be this distance divided by this distance right here. And this distance is going to be the height of this green ball, which is 1.82 in this example, or f of x plus h, minus the height of this red ball, which is simply 1 in this example, or f of x. So this height represents f of x plus h minus f of x. And then what we're going to do is divide by this distance h right here. That's what this calculation is. Notice that really the denominator is really just h. X plus h minus x is really just h. So as we let h go to 0, we can read off what our slope approximately is. And this is just to give us an idea of where we should be going. So really we've answered the question. If this really is the slope, then I could come back here and say 1y minus 1 equals 1/2 times x minus 1, and I would be done. Okay, assuming that's correct. Okay, but you never want to trust a graph or any kind of piece of technology for your answer. You always want to be able to get to it analytically. So let's do this. How do you calculate the slope of the tangent line? Well, that's where our derivative comes in by way of the limit process. Okay, and I know some of you know some shortcuts, and that's fine, but we're still developing this idea of a derivative, so we're going to use the limit process here to calculate the derivative at 1. Okay, so what you notice is instead of writing f of x plus h here and f of x, I've substituted the 1 in for the x because I'm calculating the derivative when x is 1. Okay, look, here's x is 1 right here. Okay, so that's why I've made that substitution. Now all that's left to do is to actually calculate this difference quotient and then find the limit of it as h goes to 0. So let's do this. We get the limit as h goes to 0. Now let's go ahead and let's first calculate f of 1 plus h. What will that be? That is going to be the square root of whatever is inside of here, and that simply is a 1 plus h. Okay, so there is, this right here represents f of 1 plus h. Now let's calculate f of 1. Well, that's easy enough. We could do that in our head. F of 1, we plug 1 in for x, the square root of 1 is 1, and we just get 1. And this is all over h. Okay, well, how do you evaluate this limit then? If you try to plug 0 in, you'll notice you get 0 over 0, and that's our indeterminate form that we've talked about several examples ago. And anytime you get an indeterminate form of something, you need to somehow manipulate it so that you can plug 0 in for h. And the way we're going to do this here is we're going to multiply by 1 in disguise. What do I mean by that? Well, if I multiply by the conjugate of the numerator, the conjugate of the numerator is simply whatever the numerator is, but this operation will be the opposite. Okay, but I have to do the same thing to the denominator. Okay, there you go. So really this is just 1. We're not changing the value of that expression. Okay. Well, the reason we chose the conjugate is because when we multiply these two binomials together, I only have to worry about multiplying my first terms, which is just a 1 plus h, and my last terms, which is just a negative 1. And this is all going to be over h times the square root of 1 plus h plus 1. And for reasons I won't go into now, I'm not going to distribute this h through. Hopefully you'll see why here in a minute. Okay, and don't forget to tack on your limit statement here. Here we go. Well, in the numerator, this reduces, and I'm going to rewrite this as h. 1 minus 1 is just 0. And down below I have the same thing. And now what do you notice? What else can you do? Notice that we still have an indeterminate form if we plug 0 in. Okay, but look here. H over h, this is really 1, so we can effectively cancel this out, and we're left over with the limit as h goes to 0 of 1 over the square root of 1 plus h plus 1. There you go. Okay, so now let's see if we can plug 0 in. If I plug 0 into h right here, I get the square root of 1, which is just 1, plus this 1, which is 2, and this limit appears to be 1/2, which is what we suspected. Okay, so the slope really was 1/2. And again, if you're taking an AP calculus class and you're about ready to take the AP test, I would highly recommend you stick with point slope form. There's less room for error in trying to find your y-intercept. Again, don't do more work than you actually have to. This is an equation of a line, even though most people are used to this form as opposed to this form right here. Okay, so I hope that made sense. We'll see you in the next video, where we're going to probably look at some more examples of finding derivatives. See you around.